Iniziamo. No, metti se collegato di leggermente, se no la penso che ci metti un po'.
Sì. Ok. Sì, questo si riesce a tagliare più contento. Ah, c'è un sacco di roba, si chiama Story.
Story Publishing.
Sì.
Okay, good morning everyone. Welcome to the session number 9. Today we'll listen and two case study and one project. So let's start with Clotilde and Kai. We talk about a procedure to understand the structure formation in social network using a Markov chains. We do this one. Okay.
I don't know if they can hear me. Okay. So, my name is Clotilde Nikai. I'm from the University of Tirana, and today I'm going to talk about the Markov stability condition and community structure in social networks. Okay, so individuals exhibit collective behaviors. In order to characterize this phenomenon, we try to find out the community structure into a big group of people. Actually, many real networks have community structures, not just social systems. For example, we can mention web graph networks, biological networks, email networks, neural ecological networks, etc. All of these are part of the complex systems, and all of these exhibit community structures. Community detections aims at unfolding the logical communities by only using the structural properties of the network. So, why the best example of the community is the Young Researcher Meeting. So the Young Researcher Meeting is a community that at the same time uses social media and has the logical communities by properties of the network. Sorry, if we try to define the community in order of the complex systems, we can say that community is a set of related nodes that are densely interconnected and have fewer connections with the rest of the network. It means that we have more links inside than outside the network. So, by the other side, we can define the community if we see local criteria or local behavior of the community, global behavior or vertex similarity or node similarity. But we have to pay attention when we talk about the community definition, because communities are usually implicitly defined by the algorithm that we use to adapt, and without an explicit definition. So any kind of definition that we are talking about communities, all these communities or all these definitions depends on the algorithm that we use to detect the communities. If we talk about the local definition, we have to forget the rest of the network and we have to look just for the subgraph of the network. What means the subgraph of the network? We have to try to find a smaller entity of the network that have the features that characterize the whole network. The local definition, we have to compare links inside and outside the graph. By the other side, if we try to make a local definition, we have a weak definition when we try just to compare the internal degree with the external degree of the community. Community, in the global definition, we have to look the whole community. So if we look the whole community, we must have a null model to compare. So the null model is a graph with no community structure. For example, in our study, we use Newman-Girvan null model, a random graph with the same degree sequences as the original graph. The node similarity definition, vertices or nodes are in the same community if they are similar to each other. Similarity measure can be local or global. Example, distance between vertices, agent vector components, structural equivalence, etc. are some of the features of the node similarity. Community structure and detections, we have the communities are organized in hierarchical structures. Modules may embed in smaller modules, or groups may embed in even smaller groups, yielding different organizational levels. Overlapping, each of us may be part in different communities at the same time. So in real networks, the nodes may belong in different modules at the same time that are defined by the authors mentioned. Dataset information and community detection algorithm. As I said before, we use Girvan and Newman algorithm to conclude our study. We remove the links that connect the clusters until the clusters are isolated. So, for example, this is just for demonstration. If we cut the cluster here, we are dividing into communities. How to identify inter-community links? By studying the betweenness, that the betweenness is a number of the shortest paths crossing a link. Which are the steps for the Girvan and Newman? We have to calculate the betweenness of all the links, remove the one with the highest betweenness, recalculate the betweenness of the remaining edges, and repeat from the second step. The data set that we used are gathered from publicly available data and consist on crawling the user's graphs by assessing the public web interface provided by the sites. All the data are anonymized, so are just numbers. There are no identities. This methodology gives us access to large data sets from multiple sites. In our case, the data sets is collected from survey participants. The configuration model, we applied the configuration model of Newman et al. As implemented in the Python package network X39. We suppose that two connected nodes, N1 and N2, depend linearly on the distance. The distance is denoted by D, and the attraction force between these two nodes is linearly dependent by the distance between them. Since our network follows a power law distribution, which means that we have a few highly connected nodes, and these highly connected nodes we aim to bring closer, and the poorly connected nodes we aim to push them away. We can try to prevent overlapping, but it doesn't mean that we always can prevent overlapping, because as we said, the nodes or individuals can be part of different communities or of different groups. By doing this supposition, we suppose that nodes don't overlap when the condition is bigger than 0, and then we can use dprint to compute the forces where we have the attraction force and the repulsion force of the nodes. So the network randomization, we use the Markov stability condition, where P is the probability that a node jumps from a station U to another station. The actual number of edges falling between a particular pair of vertices E and J is 1 if there is an edge between these two vertices, and 0 if there are no edges. The probability that an end of randomly chosen edge attached to a particular, it depends only on the expected degree. So the community structure, we can say that we can extract community if we can calculate the expected number of links in a random network and the real number of links in the network that we are evaluating. We have linear preferential attachment and non-linear preferential attachment. So in our data set, we used mu 1 and mu 0.75 to see how the linear preferential attachment and non-linear preferential attachment affects the community structure. Structural quality function of the network in our case study, the features that we try to extract are the degree, centrality of the network. It means if we try to interpret in social networks, it means how many people can this person reach directly between us, how likely is this person to be the most direct route between two people in the network, closeness, how fast can this person reach everyone in the network, agent vector, how well is this person connected to other well-connected people. Interpretation of clustering coefficient. A node clustering coefficient is the number of closed triplets. For example, we have two triplets here, and these two triplets, each of these triplets has 3 nodes. It means that 3 multiplied by 2, we have 6 is the number here, and divided from all the links that are in this figure here, we can find the clustering coefficient of the example of the few nodes that we demonstrated here. In our case, the clustering coefficient distribution of the sample that we used is this graph here, and the clustering is a function of the system size. Then, depending on the A constant, is as we can see here, when A is equal to 0, is monotonically decreasing. Then if we increase A, we see that at the beginning is decreasing, then the clustering coefficient in the data set is increasing. Interpretation of the degree distribution in social network, how many people can reach a person directly. Here are the data, extracted the data, connectivity distribution as predicted by numerical simulation for different stages of the evolution of the network. Interpretation of betweenness distribution in social network, how likely is this person to be the most direct route between the two people in the network, betweenness centrality distribution and eccentricity distribution that shows that the betweenness centrality is again proposed by Girvan and Newman and is defined the shortest path between all pairs of nodes in the graph that cross the edge. Interpretation of closeness distribution, how fast can this person reach everyone in the network? Here we have calculated the mean length of shortest path from a node to the other nodes in the network. For example, how fast the information can reach other nodes from a given starting node. In the second picture, we have computer simulation, computed the dynamic for the real and apparently system. So the apparent model is here and the real model or the real data are computed here. The number of communities extracted from our dataset, the connected nodes, we suppose at the beginning that the connected nodes attract each other and push the unconnected nodes apart to create cluster of connections. Communities appear as groups of nodes produced by a force-directed layout where we can denote the structural densities. From our data are extracted 8 communities, as we can see in the graph. And from this point of view, we can jump to another problem by spotting out the nodes that are responsible for the connection between the communities and the dynamic for the diffusion inside the network. Sorry. It's a small word after all. It's one of my favorite expressions. It looks just for fun, but actually is one of the main features of the social networks. The study of complex networks is still in its infancy, as we do not yet have a systematic program for characterizing network structure. We measure degree sequences, as we showed before, but we have no idea if these are right quantities to characterize a network. And there is much to be done in developing more sophisticated models of networks to help us understand network topology and to act as a substrate for study of processes taking place in network. Thank you.
Thank you, Clotilda. There are any questions for Clotilda? No? Just, I'm not an expert on statistics, I like it. And I noticed that you say that you use a Markov chain that actually has stochastic
Yes.
analysis. What do you not use the hierarchical cluster analysis? Just to observe the clustering,
yes.
the connection, the overlapping.
Yes. When we use the Markov stability condition, we suppose, we take into account that a random walker inside the community is going to stay much more longer than outside the community. So when we try to extract communities and we diffuse the Markov stability condition, we are assuming that the random walker, so when we integrate in time, it's going to spend much more time inside the community than outside.
Okay, so this was your first condition that you put into your
Yes, for the Markov chain or for the Markov stability condition of the extracting communities. As I mentioned before, even the young researcher meeting community, I think that we are all together, but just a few of us are going to keep the community continue in there. So I mean, here is the time that affects the community of young researcher meeting, because some of us maybe will go back in the conference, probably some of us not, but the organizer, let's say, are the random walker that accomplish the Markov chain stability condition, because you are going to spend much more time than us inside the community of young researcher meeting.
Yes, thank you. There are any questions more? I have just, okay, sorry.
First of all, I'm not employed in this argument, so I'm ignorance. Thank you for your interesting talk anyway. And my question is, there is a topic in this study, that topic or argument that you have not stopped in complex system. I mean, physics is a big community, but is a limit community. Okay, but there are, I think, there are
Complex
topics.
systems usually are interdisciplinary.
Yeah.
As I said in the second slide, there are many real networks that exhibit this kind of complexity. So social systems is just one of the applications. Nowadays, and not just nowadays, there are every day and more complex systems that surround us. For example, we are using, in this presentation, we use a simple model of repulsion and attraction force. This is the model, physical model. Then we are using statistics to give results, to describe the data set. And then we are applying everything in social network, because I was describing individuals. So we mapped a network composed by, in the nodes are people, and every kind of relationship between these people represents ties or links in the language of complex systems. But as I said before, I even saw yesterday, even for spacing, they are using complex systems, and complex systems is every day more present in science. In my older presentations, I used to present in a much closer group, that they were all working with complex systems. But in young researcher meeting, they were a little bit far away from, not far away, but different from complex system presentation. But I saw that the main idea is always directed to complex systems again.
Thank you.
Okay, thank you very much.
Thank you again, Okay, let's go in to the second talk, Fabrizio Ambrosino.
So, good morning everyone. My name is Fabrizio Ambrosino, a postdoc researcher at the University of Campania Luigi Convitelli and also the YRM of Naples. And this is a joint work with Luisa Stellato and Carlo Sabaresi, also from the University of Campania. So now I will show you a case study of possible radiological contamination in the low landfill site near Caserta, Italy, also near Naples. So, let's move to the introduction. The prevention of radioactive pollution, as we know, is a primary objective in the Environmental Protection Code in the operation of solid waste landfill activity. So, many studies in the recent years show and demonstrate the effectiveness of this monitoring on the main constituents of the urban landfill waste in a radiological estimation of different waste of the various environmental matrices. So, this study is focused on the investigation of such type of investigation to evaluate the possibility of radiological contamination in this low landfill site that is located in a specific area called the Litorale Domizio Flegreo and Area Avezzano near Naples, that is identified by the low 426 of the 1998 that talk about reclamation intervention on environmental restoration on polluted site. So this investigation is approved by the Campania region thanks to that document. So let's move to the aim of this talk. So the assess of the presence of radionuclides of anthropogenic origin. This work was divided in two sets of measurements. First of all, a screening of the perimeter of the area to assess the possible impact of the population through the measurement of the equivalent dose rate. Then, the high resolution gamma ray spectroscopy on several samples representative of the land field. So, gamma spectroscopy on samples of soil core of the different depth up to 35 meters, and then on samples of groundwater and also leachate that are fluid, black-brown fluid, generated from the liquid present in the west. So we have two sets of measurements, and the second set is divided in other two parts. The instruments that we have utilized are, first of all, for the first set of measurements, so the equivalent dose rate measurement, we use a portable proportional counter that is a gaseous ionization detector. Then for the second part, second point one, we have a hyperpure germanium detector, of course portable, of the Horten company for the measurement of radionuclide present in the soil core. Then, for the second part, 2.2, we have also a germanium detector, but not portable, a normal germanium detector for the measurement of ground samples, so water representative of the soil. So a normal germanium detector inside a lead sheet. So this is our monitoring sites, so the local landfill, and with the red line we denote the perimeter of the area. A landfill perimeter of about 17 meters, and an area of 200,000 square meters. So the number of points reported, the number of measurements versus the dose in microsievert per hour. So as we can see, we have a mean equivalent dose rate of 0.162 with a standard deviation of 0.072 microsievert per hour that corresponds to equal to 1.42 millisievert per year, that are lower than the worldwide average population limit, that is 2.4 millisievert per year. This limit is established by the United Nations Committee of Atomic Radiation during the 2000. So, as we can see, the higher those equivalent dose rays was measured in the last part that correspond to the to this part of the landfill that are closest to the real part of the landfill, so near to the deposition of the waste. So let's move on the second part. So 2.1, that is the gamma spectrometry on the soil core samples. We show typical core samples that are, we collected 8 boxes of soil samples in the borehole and piezometers in the survey area at a different depth, up to 35 meters. So each box contains 5 core samples of 1 meter each, as we can see. Borehole and piezometer. Piezometer are different kinds of boreholes with different diameters and also with the bottom part in contact with the ground. So for the measurement was performed, as we already know, with the Transpect, so the hyperpure germanium detector portable, and the structure that we can see is a specific appositome-made structure covered by lead layers to avoid the influence, of course, of the environment, and therefore to focus on the samples. Of course, the background was subtracted for each measurement. I can show you a typical spectra of the gamma spectrometer in the soil core. So as we can see, it's reported the main gamma emitting radionuclides, so the counts versus the gamma energy in kiloelectron volt. As we can see, the peak corresponds to the main element that we detect in the analysis. So that are the lead 214, the lead 212, thallium 218, bismuth 214, actinium 228, and potassium 14. So as we can see, we have also small quantities of cesium 157. So now in this histogram, there are the results of all 48 boxes. So the graph on the x-axis reported each boxes with the depth, the soil depth, and then the composition in count per second. So each color, as we can see from the legend, corresponds to the composition for each box. So as we can see from the legend, there are all the main presence of natural radionuclides that are main part of the natural radioactive change of uranium-238, uranium-235, thorium-232, and also, of course, potassium-14. Then, only in the first 7, 11, 15, and 22 boxes, we have also small amounts of cesium-157 on the top. That correspond to layers minus or equal than 5 meters depth. Of course, that is due to the atmospheric fallout from nuclear disaster occurring in the last 15 years on the Earth, as reported in several research work, in several papers. So let's move on the second part, the 2.2 gamma spectrometer in water samples. So we collected 18 samples of groundwater and 4 samples of leachate. Were taken in different kind of containers from boreholes and piezometer in the survey area. So how we can measure this? We put the liquids in several Marinelli beakers of 2.5 liters. These Marinelli have a hole in the middle, so as we can see from the picture, this beaker fit perfectly with germanium detector. So we can have a conforming geometry around the germanium detector. So these two box plot, this represent the statistical description of the data. So we have the median, the 1 and 3rd quartile, and also the extrema for water samples and leachate. As we can see, each result shows the presence of radionuclides also here in the water samples, but with a small amount of cesium 157 only in the groundwater samples. As we can see, we have a small quantity of these radionuclides, except for potassium, of course, and also thorium that are more soluble in water. So, result, summary, and conclusion. So the first set of measurement of the equivalent dose rate along the perimeter of the area show mean equivalent dose rate of 1.42 millisievert per year, lower than the worldwide average population that is 2.4 millisievert per year. And of course, several values increasing in the area immediately closer to the landfill. Then the second part of the measurement, so the gamma ray spectroscopy on samples of soil core, groundwater, and leachate collected at the London landfill, show the main presence of natural radionuclides that comes from the natural radioactive chain. Then the absence of anthropogenic origin radionuclides, except for small amounts of cesium on superficial layers less than 5 meters, and also in groundwater, also in small quantity. And then, so we can conclude that the dose rate is mainly due to the natural gamma emitting. So let's move to the conclusion. The results show that there is no radioactive contamination coming from the municipal landfill of Lauter, and that there is no impact in the surrounding area. So this first kind of case study can be useful for any kind of radiological experiment or radiological measurement for any kind of landfill. So thank you for the attention.
Thank you, Filippo. There are any questions? I have a lot, sorry, probably, but I will ask you just something, and we talk about it more detail probably later. when you get your measurement, in which kind of season do you have take your data, your measurement? Because it's very important. Summer, spring.
I think during the summer.
During the time. Probably your data have overestimation, and so you actually measure just in one day, in one week during the summer, 1 week.
Yeah.
It's
Depends on the measurement, because
yeah.
several measurements I remember. There are 40 hour, also 24 hours for the measurement. So we have 18 measurements, so in a week, 1 month.
Probably, I don't know, but you have to repeat in 1 year. You have to do, for example, one measure on 1 week during the start of summer, and then repeat in the start of spring. And because the data are, if you go into the box plot, then I can't better. Because it's my field, it's my. Issue. And these are the groundwater and which one of soil you don't have.
No, only
because
groundwater.
it could be interesting to use box plots also for the soil and compare it with the water. And because probably when you took the soil during the summer where the percolation, there is a percolation, there is an infiltration, so the data can be mistake. And the last one, box plot is for the box soil, because I don't.
The first one, the second.
The last one, this one.
Bleaching.
Okay. And did you see that the second quartile is the amplitude of the data is stranger, and the second quartile, did you say something?
For the potassium.
For this is the first quartile. This is the mean, no? This is the first quartile, and this is the minimum maximum, no, of the data. And you can see here is inverse. The second quartile is much bigger than the first one. The fifth.
But are two different elements.
Yeah, there are different elements, but you say that this is show you that your distribution data are different. Yeah. So you have to take more analysis, different analysis in that kind of
Not the collection of the water samples and also the soil. I don't know what is the figure, because of course I don't make the measurement of the perimeter.
Yeah.
But about those perimeter, those measurements in 1 week.
Okay.
So I know.
It was very interesting, and so I wanted to know something more. There are any questions?
Just one question. Have you discussed with your professors why is lower than the mean the value of the dose rate? Because at least it should be approximately the same as the mean dose rate. Probably, I don't know.
No, we are just investigation. This motivation for the lower than those limit. I don't know, maybe it depends on the season that we can repeat the measurement of course. Maybe.
Maybe you say at the beginning, but why did you choose this area to make this measurement, not another one?
For the first, yeah. Because this area is located within the litorale, the Mizio Flegreo and Agrovestano, that is identified by the law, Italian law for the reclamation, intervention, and environmental restoration of polluted sites. For this is
because of course important the influence of but you
Yeah,
nuclei
especially
inside
for the population
for
around.
the population and for the littoral, so because it's very close to the
Yeah, also this law is
the sea, so
last.
for this, yeah, sorry, no, because probably you have to take more sample
Yeah,
around, very close to the littoral, in order to see if radionuclei,
influence the other.
yeah.
Of course.
There
This
are
area
more-
was also amplified in the other law. So this law is 1998. So the area was amplified in the other years of course, in 2000.
Okay, thank you. There are any other questions? No, okay. Thank you again. Okay, we are almost finished. Please, maybe you come here. Today we'll go talk about a very interesting project that made Tecnomuse.
Okay. Can you hear me? Yeah. Hi everyone, I'm Enrico Preziosi. I'm a postdoc researcher here in Tor Vergata, and now we talk about Tecnomuse, that is a novel detector for muon tomography, and I will show you some preliminary results from Monte Carlo simulation about the performance of the scanner itself. So first of all, a small introduction to the rationale of muon tomography. There are about 700 million of containers that transit around all the harbor all over the world, and this number is always bigger. And but about just 3-4% of these containers are controlled to find if there are some radioactive isotopes and radioactive potentially harmful quantities of isotopes inside them. And so the idea is to find a technology that can be do a check on this container in a fast way, because the number are huge, in a safe manner, because one can use external source of radiation like industrial X-ray tomography or X-ray scanning, and in a reliable manner. Muon tomography can represent this technology to scan the containers. First of all, we take advantage of the muon that are produced naturally by primary cosmic rays, and we have a rate of about 10,000 muons per square meter at the sea level. So it means that we have a high quantity of muons that we can take advantage to use for muon tomography. And muon tomography, there are fundamentally two different approaches to take advantage of muons. To work in absorption, so we have a certain rate in a position, and if we have a certain amount of matter, the muon flux decrease in this area, but it works for a distance of the order of hundreds of meters. And for this reason, it has been used the first time to find an hidden, to search for an hidden chamber inside a pyramid, or to study underground cavities or to study the volcanoes. In recent years, was also used to check the inside of the reactor at Fukushima nuclear plant. Or the other way, and this is the way that we use in this case, is the scattering, because scattering occurs in typical size of radiation length, so just some 10 of centimeters, and we evaluate the deviation of the trajectory respect to the original one. This is the this is the relation here. So we have that the scattering strength of a material is directly related to the radiation length, and also related with the momentum of the muon. And as you can see, as the number, atomic number of the material increase, the radiation length decreases. So we have a one-to-one correlation between the material and the radiation length, and so the scattering density. So it means the animation is not proper good, yeah, but it means that we lower atomic number, we have a smaller deviation of the trajectory that increase with high atomic number objects. The Tecnomuse project has been funded by Regione Lazio and is a technology transfer of a technology well known that are RPC detector, resistive plate chambers detector, but the technology transfer to this kind of application, to muon tomography itself. There are many partners inside this project that each one has a different task because it's a technology transfer for something that can be directly used from must be user-friendly and not used by technicians. So it means that it's also important the visualization, control, and security in real application. And why we select RPC detector? Because resistive plate chambers are gaseous detectors that are widely used at CERN or at the Argo experiment in Tibet, and they have many pros in our specific case because they are reliable and good durability and can work outside, because the main idea of this project is to use this technology into an arbor, so for outdoors, completely outdoors. And also important are the scalability, the small cost per unit area, because we want to make this technology affordable for the harbors around the world, and the high time resolution that we see after, why this point is very important. So this is a rendering more or less of the current phase of the project. This is a prototype, and we take advantage of the structure given by the containers, and we have 3 containers. And these these are the detectors. You can see the size respected to a person. So we have an initial detector, the upper detector, to track the initial trajectory of the muon. The scanning container here, where we have the unknown objects inside, and another tracker to the outgoing muon tracker. So from the deviation of the material, from the deviation occurring in the scanning detector, we can, and from the variation in the trajectory, we can find, you can try to understand what's the material inside. It's important to stress that the purpose of the Tecnomuse project is not to find radioactive source, because we know that a small amount, a few grams or milligrams of radioactive source can be harmful for many years, for many people. But we want to find the shielding materials that are around this source in order to avoid some cases. This one is a real case. It's a small dramatization because it's taken from Wired, but this is a container that was in the Genoa harbor that have an unexpected high level of radioactivity, about 40 millisievert per hour at 1 meter of distance, and we see that the annual dose is about 2.4 or more or less 5 in the worst case millisievert per year. So and for about 1 year was as you can see, it's far from the other part of the harbor and was isolated because it has an unknown source inside, probably cobaltum-60 from smuggled from an hospital or something like this. So in the more general case, we can use this technology to find an unexpected something unexpected inside a container. So first of all, I made some Monte Carlo simulation in order to better understand what is the best architecture and structure of the position of the detectors. And I used a method that is in literature to reconstruct the tomography of the object that is related from the incoming outgoing traces, so tracks. So we have higher deviation, so an higher signal, so it's related to an higher value of the atomic number. The first simulation is quite fancy, but is to understand what happened. So we have some cubes and cylinders of water, iron, tungsten, and uranium. And we have here the reconstruction slice by slice. This is the first slice from the upper half, and you can see alto, that in Italian means half up. We can see the red one. It means higher atomic number, and we can see that, for example, this is water, this is iron, and this is tungsten, and we can see just the tungsten. And in the other slide, that is the central one, we can see all the features. So we have also the parallelepiped from made of tungsten, and we cannot see the water one. And again, all the different the uranium cubes are really bright. And this is the lower part that is something similar to the first one. So another way to understand what is the spatial resolution of the system was to use something that is borrowed by nuclear medical imaging, that is a bar phantom, that is a series of slabs of different thickness from 3 centimeters to 1 and 0.5, and we reconstruct with different voxel size. As you can see, with 5 centimeter voxel size is not very useful, and in this case, with the first 1 centimeter, we can see more or less the same. We can see better than 2 centimeters, but is more noisy, and so more or less the spatial resolution from the bar phantom means that we have a spatial resolution of about 3.24 centimeters. That is quite good, because we are not working in medical imaging that we want high detail, but we are working with macroscopic things. So it means that could be good, this kind of spatial resolution. So the integration time is also important, because we want to scan a container in few minutes. And so the faster we are, the better is the technology. And as you can see, there is, of course, an increase yeah, there is of course an increase of the contrast during time, but in 2-3 minutes we have a good response to find the materials. To find these are slabs from 10 centimeters thick, 5, 3, 2, and so on. So we can find a good evaluation of the materials. Previously we said why we choose RPC detector, because RPC detector has a high time resolution. So it means that since the contribution to the scatter strength is given by the radiation length of the material, but also by the momentum, it means that the additional information in the incoming tracker to understand what is the energy, what is the momentum of the muon, can add additional information. And as you can see here, without momentum information, these are some, I don't know if it's so good to see, but we have so many iron. No. Okay. Thank you. These are many bars, iron bars, and it's always a simulation. But we have many iron bars and some tungsten cubes inside. You probably can see 1, 3, 4, and this is the same image with the momentum information, and you can see more clearly the hidden triton. And it's important to stress that it's not necessary to have a so big momentum definition, but it's quite important to have below 3 GeV, about 3 GeV, and more than 3 GeV. In this case, is a good approximation. So the Tecnomuse project is over, and we are working on improving the RPC detector, so the hardware point of view, but also the electronics for the readout, and at the same time the software reconstruction, and also the software interface for the user. And the future development will be involved the use of this technology inside a real harbor, and the study of feasibility to increase the size of the area in order to scan more containers at the same time, because we say that we have a big time constraint because there are too many this huge number of containers, and but the owners of the container don't want to lose time for the control. So this is thanks for all the people involved in the project, and thank you, of course, for the attention.
Thank you, Enrico. There are any questions? No? I have one. There are any software procedure to improve the resolution of your images?
Yeah, not in terms of resolution, because the resolution is quite good for this kind of application, but of course it's important. Other software procedure, like for example to remove spurious counts, or to improve the signal, or to improve the quality of the data from in terms of material identification of triton, respect to the not harmful contribution inside. So to best identify what can be harmful or not, respect to the spatial resolution that is quite good for macroscopic application. That's it.
Yeah, I see. So 5 minutes you 5 minutes.
5 minutes, yes,
You have,
it must be the trade-off for efficiency, time consuming, and a reliable response.
This was very interesting. Thank you again, Enrico. If there are any more questions? No? Yes. Wait the microphone.
Did you tested the project, or is just in the phase of simulations and?
No, now we have the scanner, but we are acquiring many data because, of course, from simulation to real analysis, everything changed. But we have I show you that this is just one part, but these are the real detector inside one of the containers, and we are working on improve from the experimental point of view, of course.
Congratulations.
Thank you.
There are more questions? No, thanks. Thanks again, Enrico. I give the word to Francesco Stellaro.
It's Claudia, so now it's a pleasure for us to have Claudia Taccalite, who is the second keynote speaker of this meeting. And Claudio is an expert in the theoretical description of Nelson matter systems. However, today is not going to talk us about his main research topic. He's rather going to give us a comprehensive picture of the history of scientific publications. I think he will start from the very beginning, like Galileo, probably not the very beginning, and count what's happening right now. And actually, in my humble opinion, this is quite an interesting topic, given the fact that it's young interdisciplinary research. Oh well. Does it work? It's the input.
Okay, please come. Okay. Thank you for inviting me and okay. So you asked me to present me my scientific path. Okay, it's not so special. So I studied in Roma, La Sapienza. I got my PhD in Trieste, in Sissa. I did a couple of postdocs. The first was not so successful. The second was better. And after a few postdocs, I said, okay, I want to find a job. So I started to apply for research position and companies, and I was very lucky to get this position in Grenoble, in France, in a city where I've never been before, so it was very surprising. And so since then I'm in France, I moved to other city, but I'm there. I also tried to come in Italy, but they say the academic market is very complicated. But just for curiosity, I also applied for a couple of companies here in Italy after many years of research, and I was very surprised that one company offered me a permanent job and another job, but then I decided to remain in the research world. Okay, so that's my story, very simple. So today I will speak about the story of academic publishing, from Galileo to Neptune. And at the middle of the talk also you understand why I decided to speak about this, but it's a nice story, so let's start. As I also put an outline, something that I don't do usually, but I will speak about all journals, a bit of sociology and psychology, you will see why, history of scientific publishing, first after the Second World War, money, because this is the important part of this field, new journals, some curiosities, if I have time, and finally the conclusion. So let's start. At the beginning, many years ago, for sure, there were not scientific journals, so it was a life without scientific journals. And scientists were common to write, the common way to diffuse science was to write books. So you have the Principia Newton, or you have the dialogue of Galileo Galilei. And for sure, there were a few scientists in the world, so diffusion of science was very slow, and people had time to write big books with all the things that they discovered. But also there was some communication, and usually it was done by means of letters. It was the typical way to diffuse science. To give you an example, this is a typical letter that Newton wrote to Leibniz. Non ho in Italian, I can ask the translation of this part. And so you can see Newton want to explain the foundational calculus. So I say, the foundation of this operation is evident enough, in fact, but because I cannot proceed with the explanation of it, I have preferred to concept it thus and write this strange code that is an anagram that you can decode and try and see how the theorem of calculus was understood by Newton. So this is a typical way of communicating, because scientists were really, for them was very important the priority to show that they were the first to discover something. But they don't want to spoil, if you want, the research of the others. So this was a typical way of communicating. Moreover, you have to imagine that Newton also spent quite an amount of time studying Bible, and because at the time people were convinced that the Bible was like an anagram wrote by God that was very natural. So it was very common to write an anagram. This is the typical way to diffuse science. But then in 1665, a lawyer in Paris decided to create the first scientific journal. That is the Journal des Savants, then changed the name. Okay. So it is Denis de Sallo. He was supported by the minister of the treasury minister, the minister of finance of the time, that was Colbert. And he opened a journal that was way to collect reviews of all the books that were published in that period, news about the discoveries. On this period was discovered the blood circulation, the digestive system, the path of the comets, and so on. And it was very important because it was a collective enterprise in the sense that De Sallo hired many people from other countries, from Holland, from England, as an editor to collect all this news and so on. And he also made the journal in such a way that he didn't want people that are from too strict, from community that are not based, people are not based on facts. So he didn't allow to Jesuits or to Cartesians to publish in his journals. And this was a problem because they made pressure, for example, on the Nuncio Apostolic on that time, and so he was obliged to close this journal. Even if then Colbert gave him a job in the Minister of the Finance, and the journal was reopened after some years, but with a more natural person. Royal Society, after a few months, opened a similar journal, the Philosophical Transaction Journal, and that is still active. So this is the oldest active journal that exists. I also published a paper on this journal. I don't know why, but okay. Once they ask a review, some colleague and they can publish on this journal. And notice the motto of the Royal Society is Nullus in Verba. That is the same idea of De Sallo. So things have to be based on facts, not on the words. So you need the proofs to publish something in these journals. So why journals became important for the scientific community? But for sure to diffuse science, but also for another reason that was because, as was pointed out by this sociologist, this Robert Merton, that studied the sociology of scientists. Okay, you know, but you are like guinea pigs for other scientists. So there are psychologists that study scientists, there are economists that study the economy of science, and there's also sociologists that study science. And what he pointed out that scientific journal, the main advantage of scientific journal was to reduce the wasteful publication of scientific effort. Because before journals, things were discovered many times. And all scientists, many of these simultaneous discoveries ended in dispute. So you can see 92% of the 17th century simultaneous discovery ended in dispute. 72 in the 18th century, 59 in the first half, and only 33. And this was like the diffusion of journals, so because you can find that something that is already published, so it's okay, so we know who's the first that discovered something. This was the big advantage, the invention of the scientific journals. He also studied the psychological and sociological effect of this. For example, say that all scientists have this Eureka syndrome, so they have deep concern with established priority. You have to be sure that you be the first to have done something. And that's something that journal helped to do. And moreover, there was the typical phenomenon of artists and scientists that in psychology is called cryptomnesia, that is the unconscious plagiarism. It means that you read something some years ago, and you forgot that you read something, and you rediscover it. Okay? But you don't do it, but it can be conscious or unconscious. And for example, Hamilton, the mathematician, wrote this sentence: as to myself, I'm sure that I must often reproduce the things that I have read long before, without being able to identify them as belonging to other person. So it was a common problem that was solved by journals. But journals also had also a side effect, so was pointed by Merton, was they enhanced the role of genius, because when a discovery is done by many people simultaneously, it means it was not too difficult discovery, because all the labs were very close to discovering it. Image in recent time, the discovery of graphene. There are lots of people that claim that they discovered in the same moment they got the Nobel Prize. But the discovery was very easy to do. So it was a scotch. Yeah. So the problem was not, but when there were not the journals, you can measure the simultaneous discoveries. With journals, you cannot measure anymore. So everybody that making discoveries is a genius. So you cannot distinguish between different discovery and easy one. So this was the beginning of the journal. Now how they evolved. But the evolution of journals until the Second World War was quite slow. In the sense, scientific publishers were mainly scientific societies or learned society. There were some publishers, but they were usually broke. They were not successful. Also, the public was not so large, so it was not a big business. They also were printed in cheap paper and so on. And also, they were not important because before 45, the reputation of scientists was based mainly on membership of appropriate society, meeting with people, demonstrating their knowledge in public, and so on. It was called a gentlemanly reputation. But then everything's changed because different countries start to put a lot of money in science. First of all, with the Second World War, I think to the Manhattan Project, all the money was put in science. And also after the Second World War, with the Cold War, so there was a lot of money in science and a lot of scientists, and things changed a lot. First of all, the academia grew a lot. This is some data from UK. So in higher education institutions, the higher education institutions were only 31 in 62. They passed to 162 in 2015, and the permanent staff was 4,000 in 1955, 200,000 in 2015. So the number of scientists grew really a lot. And moreover, there was an expansion of academic publishing. So from 10,000 journals in 80 to 62,000. And also there is a very fast growth of number of publications. It was estimated that the growth in scientific publication is exponential, with a doubling rate of 15 years. That is a lot. Even if, okay, then on the exponent there was a discussion, but more or less the doubling rate is 15 years. And from 70, there was also the introduction of database, so the switching to people start to count citation, fact, all these things. And what is the consequence of this? But first of all, academia jobs, they got a structure. Before 35, everybody was a professor. But then they invented the lecture, senior lecture, assistant professor, associate professor, different levels. And then you have to evaluate people. So how you give them a job or a position. So the easiest way to evaluate people was to use the research output as an indicator of the reputation. And there is also the funding. And the reason that teaching is very difficult to evaluate. So you cannot say, it's very difficult to say who is a good teacher, who is not. First of all, for example, if you ask to fill the forms of the student after the course, this is really not a good measure. You can show that some studies show that even if a professor is very well evaluated by students, can be not a good professor. Maybe he's very nice person. So you say, oh, this professor is very nice, and can give him maximum mark. So research output was for economists, but also is a very simple way to do it, very easy. So you have numbers. So numbers can be counted. You can count citation, number of publications, everything you want. So you can count. So all the reputation was switched to research output. And the money spent in journals rose really a lot, from 42 million in 93 to 108 million in 2014 in UK per year. It's an increase of 280%. And if you want a comparison, remember that the FPI, that is the price of the goods, I don't remember in English, but okay, this like product internal order, the increase is only 82% increase in the same period. So the price of journals subscription is really low. Retail price index, okay. So but if you want to understand really how the market change, you have to know, I have to present you the story of Maxwell. It is not the Maxwell that you know, the one of the electromagnetism, but it's another Maxwell, a very smart one. It's this guy here. He's a Robert Maxwell. Albert Maxwell was born in 1922 in a Czech village, and he served in the British Army during the Second World War. He got citizenship, the British citizenship. He was speaking 9 languages. For this, he was hired also from the intelligence service, or British intelligence service. And after the war, he started working for Springer, and Butterworth, who was another publisher. His dream was to be a millionaire, I can tell you, just from the beginning. After some years, he made enough money to buy Butterworth for this editor. And he changed the name in Pergamon Press, so the Greek city of Athena, the goddess of wisdom. In a few years, he developed a very good strategy. He understood that it was a period where science was really expanding a lot. So he was traveling all around the world, convincing important scientists that their field was very important and deserved a new journal. And so he was opening new journals of everything, new journal, nuclear something, new journal. He started to open many journals. And also he understood that the market was so growing so fast that the reality was not competition. For example, North Holland in that period was published a journal called the Journal of Nuclear Physics. And without problem, he opened a journal called the Journal of Nuclear Energy. But there was no competition because the number of publications was increasing so much that there was space for all of them. In 1957, Maxwell was also able to negotiate the English version with the Russian journal. That was surprising because ultimately there was a Cold War, but he didn't care. He was able to also negotiate with Russian anyway. And in 1959, Pergamon published 40 journals. 60 years they were 150. Also, he got a very good result that he got from Japan, so that period were struggling to publish in English, gave him all the rights to the publication for free, just to have an editor, an English version of the paper. So he was very successful. Imagine he was using going out with Rolls Royce, offering important dinners to scientists. What do you want? He wanted a big villa in Oxford. He became a millionaire. In 60, he was already a millionaire. Then, okay, his story was not successful at the end because in 1984, he started to make questionable investment. He bought a couple of football teams, television station, the UK Mirror, the New York Daily News. So he lost a lot of money. At the end, he sold Pergamon to Elsevier for 990 million pounds. But, so this is the guy that gave the shape to scientific journals, as we know. So they transformed scientific journal in a business, in a big business. But it didn't have that, because there was other people that also entered the market. And in particular, one thing that Max didn't realize was the importance of impact factor. Before 1974, publishing a journal or another was more or less the same. It was not so big difference. It was more like a journal were like a passive media. So you did some research in something, you choose from one journal another according to your sympathy or the one that you like more. But then it arrived Ben Levin, that is a biologist that created the cell. That has a journal with 35 impact factor now, like more than nature. The idea of Ben Levin was that to publish journal that solve important questions, so big problems, full stories, not just that report an experiment, something about a measurement and so on. So it was the first time that an editor discovered more articles than he published. It was the first time that someone did it. And he was very successful. He created the high impact factor journals. And from the same period, also people start to use this impact factor metric that was created in 1960 by Elgin Garfield. So what's happened then? These companies continue to grow. There were some merging. For example, Nature Group and Springer merged together in Springer Nature. Bergamo was acquired by Elsevier. And I just want to report you this sentence from the CEO of Elsevier when he bought Bergamo. So you have no idea how profitable these journals are. Once you stop doing anything, when you're building a journal, you spend time getting good editorials board, and then we stop doing all the stuff, and then the cash just pours out, and you won't believe how wonderful it is. Which how much was happy this guy. He got good Bergamo journals. But at the same time, learned society, scientific society, try also to reorganize themselves, to expand. And in particular, in physics, I put two examples. The APS create many journals. Now they are 14. And in physics, it's very successful compared to the commercial part. So this was a very good initiative. On the other hand, in Europe, there were many good journals like Cimento, Journal de Physique, Physics, that decided to merge together to create a European Journal of Physics. That was not successful at all for bad management and so on. I don't know how many of you publish in APJ, but it's very, I think it's very bad quality. So from this side of the Atlantic, it was not successful. On the other side, it was very successful. And then the story continued to evolve because in 2000 there was another revolution in this field. That is the creation of open access. In 2000, Patrick Brown, as a biochemist, and Michael Eisen, a computational biologist, they created a public library of science, PLOS. Then opened the first successful open access journal, that was PLOS One. And the idea was that, I think they have a very good idea. First of all, that papers should not be excluded on the basis of lack of perceived importance. So they publish everything. It was not a selective journal like Cell, Nature, and so on. No, it's an open journal. If you do a research, if you don't discover the most important things, you can publish in PLOS One. And also they wanted that the price should be not so high. So publishing PLOS One is $1,300. So it's not so expensive. The other publisher didn't believe that this can be successful, this idea, at the beginning, that it can be sustainable from the economic point of view. But instead it is. And the number of, open access papers start to increase and increase. This the number of publications per year, and you can see the number of open access here that is growing with time. So more or less from when they create the PLOS One. And in fact, many publishers when they saw that +1 was working well, tried to copy it. Nature was the simple example. They created this scientific report that has the same price, the same idea, so just to make competitors of +1. Let's say that Nature then were very smart because they understood that they can create high impact factor of an access that so they get more money. So what is the situation today after this review of the history? But the situation today is that 5 publishers, these that you can see here, control 50% of the market for all scientific publication. It was raising from 20 to 30 to 50 still today. Let's say that some disciplines have escaped the control of major publisher. Art and humanities, mainly because the language barrier. So usually, we people that work in humanities publish their own native language, so Italian, Spanish, French, and so it's more difficult to get a big company in this. And physics, also biomedical research, but I'm taking the example of physics until now, because scientific society were, maybe IPS or other, were well organized to be a competitor for this commercial company. This was, okay, I put a lot of references in this presentation. This was a study by Lariviere and on the market of scientific publishing, and as he point out that as long as publishing high impact factor journal is a requirement for researcher to obtain a position, it would be very difficult to fight against this market, if you want. In particular, for physics in the last years, I think Nature was really became a brand. I mean, it's like you buy Nike shoes or Lacoste. It's the same. You have to do. You need the Nature in your CV. I mean, it's really you have to pay to have Nature. And so they create low quality open access, high quality open access. And then open access to make happy many people. I have some colleague in La Sapienza that is very happy to publish on quantum materials. I was very surprised with this. I never heard of this journal. They said, oh, I publish on quantum materials. It's good. And then they created a list of journals. And so, because they have to, we want to try to keep, to take the physics, the market, the market of physics. Now let's look to the economical point of view of these journals. So why scientific publishing is a remarkable big business. Now let's have a measure of this. With a total global revenue of more than 90 billion every year, it went within recording and film industry. So it's larger than all the music in the world, the amount of money, less than movies, so it's not bad. But it's more profitable. Why? Because, for example, Elsevier in 2010 made a profit margin, that means the money that you gain when you remove all the expenses, of 36%. That is a lot. It's higher, for example, than Apple or Google. Apple or Google earn less money selling selling iPhone than Elsevier selling journals. And this margin rise to 40 in 2013. To make a comparison, a journal that are published by scientific publisher like ABS have a profit margin of 20. University publishers are 25, and normal journals that you can buy, The Economist, Donna Moderna, whatever you want to buy, have a margin of 12-15%. So it's great. Publishing scientific stuff is great, it's much better. And why is it so successful? It's so successful because it's called a triple pay system. So, government found scientists give the result to publish it for free, scientists peer review the manuscript for free, publishers sell the product to library that are funded by government again, and they pay another time. So the government paid 3 times for scientific journals. So it's great business. You don't have to pay who write the papers to correct it. It's great. Now, in the last period, there was also a pressure to switch to open access. What about the money of open access? But let's say that, first on the list again, directly here. Open access usually has a lower publication cost because they are only online. There are many, often new companies, there's a better workflow. So in principle, if we switch all publication to subscription on journal to open access, we will save money. In reality, this doesn't work. I mean, when publisher propose open access, they know that they were not going to lose the subscription on journal. So people start publishing both of them, so they don't need even more money. They also many people were thinking that going online should. I saw some economists that suggest not to buy shares of the publisher because now internet will destroy them. No, they need more money on this because they start to sell subscription to a group of journals. They sell the research, the statistics, everything. So they got a lot more money. Now, open access can be a solution, but unfortunately, we should close all the subscription on one if you want to save money. And moreover, open access has a nice effect that more you pay, the higher is in the impact factor. So this is a typical plus one that I showed you before, that has an acceptance rate of 70%, it costs $135. If you want physical regulator, you want physical RXC, you want open, you pay $2,070. And if you want to know how much it costs a nation, this is an estimation made by the Nation Group. If Nation was open access, you should pay $30,000 for each paper. Also, critics that is always made to open access that they have the pressure to publish as much as possible because more you publish, more you get money. So, which are the solution of this market? So, some people start to think that probably we should reorganize and create something new, something different, and to bring some money back to science and not to the publisher. So today I will also spend time presenting a journal. That's also the reason that motivated me to make this presentation, but also other journals that similar initiative. So I work as editor for a journal that I would say a very nice idea, but it's an example because there are many others. We present also the other. It is a side post. The idea is to create a journal that is okay. The web page is not fantastic, but it's there. The idea is to create a journal that is green open access in the sense that people that write authors don't pay to publish, and readers they don't pay too. So, but it's not a miracle. We need money. We need money, and so the way to get money is to ask to university and funding agency and so on. So at the beginning, this journal was founded by the Netherlands Physical Society, then got some money from French university and from UK university and so on. So until the university decide to continue to found this journal, it will be free for all scientists to publish on it. Also, the idea to review and accept paper is so I want to just present a couple of advantages. So, okay, as I told you, it's two-way open access. It's managed only by scientists. It's good. It's not profit, so not commercial idea. So all referee reports are public. You are accounted for referee, and also it is possible to comment and continue to write about the paper even after the publication. And the things that I like also this idea of this journal is that as an editor, I cannot accept the paper. That's great. I got the paper, I sent to referee. So submission is a true archive to save money because they have very good server. I got the paper, I select the referee, they give a report, I write a recommendation, and the random selection of editor in the same field decide if accept or not the paper. So it's not directly the editor that has the power. The editor has only the role to interact with the referee and to make its recommendation for the acceptance or rejection. I think this was good. And after publication, it's possible to comment and so on. So this I think a very good journal is working. We have got many publications. It's not the only one, so I will briefly present you also other initiatives. And in particular, was recently created a quantum journal, has the same philosophy of SciPost, but you pay like 10 euros for each paper, and you can pay up to 100 or 200 euro if you have money. Otherwise, they accept anyway. So the same philosophy of SciPost. Another thing that I like is the Fair Open Access Alliance. There are different journals in this group, also from Journal for Mathematicians. And also there is the idea that in an open access journal, should not be the authors that should pay the fee, but the institution. Because if they are the authors, if one author has money and another not, you cannot publish. But if the institution or the university decide that we found some 100 papers this year, it's the institute, they ask money to the institution, not the authors. This is okay, the idea. Another journal that I like also, it was created recently, was Science Matters. The idea of journalism is a bit different. It is that imagine that you discover that at a certain moment, if you give to a person a green tomato, you can cure the fever. So you make a statistical test to say, okay, the green tomato can cure the fever. You cannot publish the result on a journal because they will ask you, okay, but which molecule has the effect? So you cannot write the green tomato. So they will ask you the story. Instead, the idea of Science Matter is to publish, okay, you may like or not, but to publish results that are significant, so with statistical relevance and so on, even if you don't have a story, so you don't have an explanation, but you have a solid result. And this can happen in all fields. So you are making measure of something, you say, okay, but I measure that the transport of this material is very efficient, but I don't know why. You are not obliged to invent a story or to make a fantastic hypothesis. You can publish on Science Matter. And finally, also another that I like a lot is Chemistry Squared. It was created in Barcelona. And the idea of Chemistry Squared is that it's an open access journal. You pay to publish papers, but since it's not profit, the money that they got from the journals can be used to support PhD students and postdocs. So you can apply also for fellowship here. So there are PhD position, postdoc position that are funded by the journals. That's a very good idea. I have 5 minutes, so I will be. Now, okay, my talk is finished more or less. I put a couple of curiosity because I like curiosity around the world. So, okay, I will do very fast. First curiosity that, okay, there are people that may live without scientific journals. So the question can be strange, but I want to show you a couple of examples of people that are working without scientific journals. First, an example that is quite weird, but I like it. For example, there is, I don't know if you know the story of Perleman. There's a mathematician that discovered that solved the Poincare conjecture, and he showed that, okay, you can publish, he published everything on archive. He never published his solution on any journal. So his idea was that if everybody was interested in how I solved the problem, it's there, you can read it. And you can think that this is a strange case. But usually, as editor, I got a paper where the editor say, the paper is already quite popular and it works also as archive document. I submit it to your journal only for sympathy. If you want to accept it, it's fine. If you don't accept it, it's fine too. We accept the paper. This is a professional moment. I cannot tell you where to put the name. Another initiative that I really like a lot is the Polymath blog. It's a blog where people solve difficult problems in mathematics all together. You can join and participate in solution of the problem. And then they also create papers at the end, but the solution is there on the blog. I advise you to not to go to the blog because it's useless. I mean, it's a very high-level mathematical problem. I don't understand the word of these problems, but okay, yeah. And this I will skip. And now, last curiosity that I want to show, this journals are all based to make their reputation journals are based on citation. So discover DNA, the relativity, the quantum mechanics, and all the, you have an idea which are the but also
Scientific programs.
also at the end this is a list of the most cited scientific papers. If you want to be the most cited, you have to have more than 12,000 citations. This is the first one. 359 citation is a method to quantify the number of proteins in a solution. And then you have so the idea that these are all groups of most cited problems. The idea that the most cited problems, the most cited papers are the ones that are useful to other scientists. That's the philosophy. So there are statistical methods to study population, there are software to analyze gray patterns. This is great. This guy made the list of the range of the ions. It's something very simple that is used by all crystallographists to what they wanted. 1,000 most. And then, okay, the FT, the software package, statistics applied to phylogenetics. We have lots of Italian scientists, Nicoletta Sacchi, that published a fast way to extract RNA. It's one of the most successful papers. So this is the message. Installation, what you want to devise a method to make it possible to make new experimental calculation. But don't discover new science because you get very few citation. Cioè, discover DNA or very few citation. So to conclude, okay, green open access can be a valid alternative to open access or subscription journal. I don't think they will substitute the normal journal, but I think they can push them to low the price. Please don't work for free for big publisher because they are making a lot of money. At least unless you are a shareholder. So if you have a lot of shares of Nature, so I understand you want to work for Nature for free. That's the reason. So this is from a report was for the UK government to change the publication system, and the view that makes this report say that the moral courage and commitment required to publish research outside established prestige generating channels proved too high to be a too high barrier for most academics. So that's the reason why more publishers are not successful. It's okay, the figure from Scienza Quarta, and that's all.
Well, I'm sure there will be quite a lot of questions for Claudio. Not really? Please.
Just a curiosity, how much is the impact of this issue?
It's new, you have to wait 2 years to get this on factor. I can't see
All the others, for example, the first one you were mentioning,
the
cost, the other one.
No, the other, I didn't check. I didn't check. Okay, this one, I didn't check the impact factor.
There's another question from the back.
I'm actually just an intruder. I'm not sure I'm allowed to ask questions, but anyway. So the first comment is SciPost. Is it recognized by Scopus or Web of Science?
Yeah.
Okay, that's good, because those are the rules of the game.
But all of them are recognized by Scopus, Web of Science, they have a yes and number of time.
That's it. And just a comment. So I work in the UK, and someone argued that considering that the research is financed by public money, also the results should be public, so that all the community can benefit if someone has the will to go and pay for them. So I strongly agree with the fact that all the results should be open access, and I appreciated much this green open access opportunity, because if you try to go and open access to some of these ABS or some other journals, £3,000 or dollars are not so cheap. So my comment was we should have all the results open access for all the community to benefit from them. So, thank you.
There's another question.
So what is the idea of bringing back the money for science? Like you said that these signposts and all these things are actually have an idea to bring back the money to the scientists. So how a signpost is bringing back the money?
No, but when I say bring back money, is that you don't spend money to publish. So in that sense, you save money. In this sense, bring back money.
Okay, because chemistry is
No,
where
no, yeah,
that money actually.
You know, this is really an exception. This really bring back money since you can apply for PhD fellowship and postdoc and so. This is really another way to do it. So you publish, you pay like, it's also not so expensive like an open access journal, but then there is a possibility to apply for fellowship. So it's a good idea.
For a lot of us, we're young researchers that are maybe working on our first or second papers. Do you think there's some advantage to us publishing in an open access journal versus publishing in a traditional journal?
Yes, there is an advantage to publish in open access, not only in open access, but in general open access. The paper in open access, in average, got more citation than in subscription journal. There was some test of BNAS or another journals, and you see that on average, the open access one, with respect to the subscription, got more citation. Probably because people find it more easy, just click and open it.
Other final questions?
So just like I said in response to what Derek said, I was wondering why we should publish open access journals if archive exists. We can put an archive and publish in a traditional journal.
I completely agree with you. John, my opinion, you can, especially in physics, you can put your paper on archive and then send it to some journal or just after. So there is, in this field, there is no need for open access in some sense, at least I would say in physics. But in other fields, it's not like this. For example, in chemistry or biology, they don't allow you to put the paper on archive before it's published and so on. So there is an idea to try this. So it can be important in other fields.
So why should we publish it all in journals if archive exists?
What?
Why should we publish the journals at all if we can put our results in archive?
Because I agree, but I think then it would be, I don't know, you can try, but maybe I think it would be a mess, that would not work, because
Because it actually works.
probably even if there are many critics, the review process, I think it's pushed to like a small improvement or check of the paper, so I don't know if it will work in this way.
Let's move to the, let's say, last three questions. 1, 2, 3. And I'm sure Claudio will stay.
Thanks. Do you think that another way of getting back money can be to focus on companies who use who does massive use of scientific results, like for example Apple or something? I mean, in particular, technological companies who now base all around the world really low taxes. I mean, taxes should be really higher because the price, the investment is so risky in science and so is socialized by government, funded by government. So the money should be. And do you think this is a good point? And then use those monies to put them in science again. I mean,
I strongly advise you to read the book of Mariana Mazzucato. That is an economist working in the UK, also is an advisor from the UK economy minister. They wrote a book exactly about this. When we show that Apple, it's great. iPhone is made of all discovery made in public laboratory in the US. I mean, tactile monitor, Siri, it was financed by public money and the education. It's incredible, and then they don't pay back any money. Also, pharmaceutical stuff. This Taxol, that is one of the medicine for cancer most Taxol most used. That they got 0.5% of revenue. The public laboratory that discovered the molecule. So
Yeah, it's crazy.
It's crazy. No, you can find. Yeah, this is great.
I was wondering, you showed us a picture of the past and the present. Concerning the future, do we expect the number of publications to still rise exponentially, and also concerning the green, gold, open access, or what do you think will be the picture in the future?
In the end, nothing can grow exponentially because this has to stop. I mean, the earth is finite, the number of scientists also are finite. It didn't stop yet, so it will, and yeah, probably very constant. No idea. I don't know.
Okay, we have time for a very last question or comment.
Again. No, just a comment. European community actually or European funded projects asks open access, and they get very much annoyed if we publish in journals that are not open access. So this, I think, will change anyway the way of publishing. The problem is that I will see a bit improvement, because this means that we have to pay some part of the budget of the project in order to put it in open access.
If you count money, the money that university and research centers spend in subscription of journals, okay, they make some estimation, is higher than if they convert all the papers in open access, probably they will save money. So,
okay, universities will save money, but we pay.
University should give you some money. I mean, the idea that if a university oblige all of you to publish in open access, they should stop to buy subscription of the journals. They should give this money to researchers to publish. If they don't do like this, is a problem.
Yeah. But anyway, the important message is that Europe wants grants.
Okay, so I would really like to thank Klaus again for this awesome talk. Please to ask you questions even during the coffee break, which starts now, and we ask you to come back sharp at 12 here. And Claudio, a present from this prestigious university. Per ringraziare questo lavoro gratuito. Però allora ci dobbiamo scusare, vabbè, l'abbiamo entrambi già dato, insomma. Grazie.
Questo lì, guarda, la storia di questo Robert Max, c'è Rostro,
Che devo dire? Sì. No, sarebbe stato bello. Ah, sì, poi vediamo se incastano. So, is there, okay, one is you? Yes. Yeah, the last one. Yeah, I'll be in. Okay. I have some visual data in the PowerPoint presentation, so if let's see. So if it works with the Darà uno studio sulla soddisfazione. Lo chiedo? Last but not least.
Like to the extent that I know what's expected out of me, but I don't know how to make it any different.
Go what you can. Sure.
No, it's fine.
Oh, you already did? Yeah. Let's see. Apparently, it was not visible to the Mary's laptop. No, it was. Just yes, that's it.
Ma ci rivediamo dopo, quando dopo il direttamente la
Io ho studiato qua, abbiamo parlato di descrizione forse che hai scritto dopo 2 minuti che saranno risentiti. Ok. No.
Guarda, secondo me
Ma questo nuovo contingente dipende da
for sure però tu ci devi anche applicare
It's really easy to switch. You can leave there. Yes. We do it. Just for fun. It's not gonna kill us. The chair.
Only there is no plugin for that. I remember I have to install something. Okay, please share. I have the share.
So you can. If that's the only way, maybe I will ask you to leave it connected and then you just switch the source. If you don't need the. Can you check it?
Yes. So can I have a contract? It's the latest version of this.
Yeah. Can you?
La ragazza invece da 4 c'è stato quello scudo mi dice quando sono perché non hanno un mezzo
Se uno fa una media con tante persone, poi possiamo codificare qui per togliere le ali, puoi fare quello che vuoi, ma non ci abbiamo
ma pure per esempio c'è questa è una ragazza che questo mi piace molto se come ha fatto se non è spazio con questi nuovi non sono d'accordo però ripeto a me
l'unica cosa che non mi piace però è che sei riuscito ma uno scudo, cioè per me è uguale quanto
ma effettivamente io mi posso sicuramente che sei una linea che c'era questa poi c'è che c'era il 5, c'era il 4 e c'era il mezzo
non sono metodo con
no, quindi però questi tre hanno messo
vabbè Questo è... Allora, effettivamente se uno volesse fare bene, io vedo la definizione dei fatto ristoranti, no?
E se per il balto?
No, però non si segna reale, dice ok, come una cosa così, uno 2, gli altri 4, 4, 4, 5, 2, 2, 4, 5, 2. Però non c'è più tempo, non è abbastanza statistica da questa cosa. Quindi, qual è il problema? Chi è che c'è?
Il problema è però, esatto, però sono d'accordo con nessuno, quello che io so che non mi piace, però facciamo tutti separati,
Se c'hanno delle approach, vedi, cioè, il problema può nascere se ci sono, se c'è un altro che c'ha, mi dice,
io ho selezionato il posto che non è più faccio un vedere c'è questa che tre con una classe e c'è quella che il posto è che dice tanto funzioniamo c'è
continuano bollato.
Solo per dire, facciamo tutto questo.
Yes. As soon as if you have it on the pen drive, I will start. I'm using my machine too. Is it working on your machine? Yes. You can just take it because in the meanwhile I will.
Tra un po' ti porto anche i così Max allora.
Poi io ti passo la parola, non è che sei così per me. Io chiudo la sessione e poi cambio.
Vabbè, quasi tra 5 minuti che ricordo.
So, which one?
No, yes, this one.
The second one?
Yes, this one.
Look. So, for both of you, I will let you know when 5 minutes are. Yes. 5 minutes to the deadline and 2 minutes, and then I will stop you. 15 minutes after.
We have to stop, we have to talk mostly 15 minutes at most.
16, I will let you finish what you're saying. But not 20, so then it's.
No, of course. Okay.
Okay, let's see. So you can take your time. Let's see if it works.
Just screen share.
If it's,
I
think it's visual. It's not there. No video. Second, no, it's there. Try to make your footprints.
So the presentations are on the desktop too?
Yes, you will find them.
Okay.
It's already there. Okay. There's nothing special you have to do.
Yes.
Okay. Since I was sitting, it's not a problem for you. You just leave it here connected to the cloud. No problem. So I just change it. Thank you. That was it. Go back to HTML. Okay, go to the coffee. Yes, please join us. 10 minutes. Yeah, we'll start in 10 minutes. Okay, super.
But in Windows, when I do it, I just do like this. I cannot see. And
It's not, did you try? Io intanto metti. No, dico, cioè, il Windows, non so.
Sto passando la parola. Sì. Ma la presentazione sei riuscito a mettere? No. Well, then you
And then we try, like, we try.
tried, but they didn't.
If Emiliano tried and didn't succeed, I don't think I can do anything better.
That's okay.
It's keep your note, I'm not so shocked about
Yeah,
it.
exactly. Yeah, you make modifications. It's too bad for you because it's not to try to connect another laptop, but then it's going to take too much time to
No,
change.
no, it's okay.
But it should be. I mean,
Just the timer must also do.
The timer, I'll be your time. And in any case.
It's not a problem.
There is a problem. Well, yeah. Anche della mia mail lo prendi da solo? Non è successo?
The problem is like
La mia
I
pennetta
have some
diciamo
notes
presentazione
which will not be visible in the screen but on the side or the which I will be able to see.
Do you have it on the pen drive? Emiliano, can we use also for and I think you have the Ashwari thanks you.
Thank you.
Or if not, Lorenzo, we can also ask the hero to use his laptop if it doesn't work from.
But I need the.
Well, since you have, now it's our laptop.
Some usefulness.
because here it's is it possible to see also quality or not?
You can, so.
Yeah, no.
You can copy just outside. It's on the video.
So and then animation,
Slideshow from the beginning.
yes. You want to see also the as a presenter viewer.
This part I will be able to see across it.
Oh, okay. Then we just want to share the screen.
No, also yes,
That's
downward.
the problem because it's middle in the screen. It's not the second screen. Which is why it's not good.
We can change it from here.
No, but yeah, it's.
No, it's okay. I mean, it's
Yeah.
okay for me. I mean.
Okay. So, extra omnes. Grazie. You can stay here.
This is connected.
Line is connected. You should have tried this way. Yeah, see this one. Just ask. Just a second, we'll get everybody in and then we'll start. Science.
I'm so impressed by the fact that there are still that many people around, which is good, and the fact that it's the last session of the meeting, which is dedicated to quantum physics, and we'll see different applications. So, well, there's no reason not to start now, and the first speaker of the session is Aishwarya Nagar from Room. Please, Aishwarya.
Okay, so hi, I'm Aishwarya Dhar from University of Rome, Torvarada, under the supervision of Professor Silvia Morante, and today I'm going to talk about the aggregation process of A-beta peptides and the effect of beta sheet breakers using a post-grain molecular dynamics approach. So the outline of my talk is, I will tell you what our protein conformational disorders are, of which Alzheimer's disease belong, the beta sheet breakers, the small peptides, how they affect the aggregation process, how the post-grain molecular dynamics approach have been used and not the all-atom for this type of simulation. Of the known post-grain model, the Martini model, Martini force field is a well-known model, and we have used, I'll tell you a description of the Martini model. So there's a drawback of this model, and that the secondary structure is not been possible to see by this model. So the Go Martini approach, and then I'll give you an outlook of the work. So what are protein conformational disorders? So a disorder in which insoluble protein fibrils which gets deposited in the tissues and organs of the human body and which impairs their functions. So how are these fibril formation takes place? So the native proteins molten in molten globule or denatured proteins form self-association, which forms an amyloid core structure. So protein aggregation characterizes neurodegenerative disorders. On the right, we see some of the protein conformational disorder diseases and the peptides which are part of this, which causes the aggregation, the respective peptides. So what are Alzheimer's disease? It's a neurodegenerative irreversible disease. It causes memory loss and some behavioral issues. So it has two kinds of lesions, mainly amyloid plaques and neurofibrillar tangles. So the amyloid plaques are almost spherical shaped deposits of amyloid beta peptides, and neurofibrillar tangles are helicoidal shaped fibers composed by tau proteins. In our talk, we are focused on studying the amyloid beta peptides, which changes its structure from helical to beta sheet and is prone to aggregation. So, how are these amyloid beta peptides formed? These are derived from large transmembrane proteins called amyloid precursor proteins, and it is being cleaved by enzymatic cleavage by two secretase, alpha gamma secretase, which cleaves the large membrane to form not harmful peptide called P3, and beta and gamma secretase which cleaves this APP to form A beta peptides, which is a harmful peptides. And A beta peptides have the tendency, as I said, to form aggregation. So is there can one develop a molecular strategy to prevent such aggregation or fibril formation? So these small peptides called beta sheet breakers, which inhibit or delay conformational transition of A beta peptides, and these are designed to mimic a portion of A beta peptides. As we see the sequence of 40 amino acids of A beta peptides, it mimics the central portion of the A beta peptide. So the effect of these kind of peptides on A beta aggregation has been tackled both by experimental and computational approaches. So what is a molecular dynamics simulation? And we have used molecular dynamics simulation. It's based on
Newton's equations of motion, and the force is derived, is given by the derivative of the potential energy function. So when we have the initial position and velocity of the atoms, and then we get the force, we get the potential energy, and then the potential energy contribution to is the most important part in molecular dynamics, and these are the terms which contribute to the potential energy. These are bond stretching, angle bending, dihedral torsion, and non-bonded interaction. So in the first term, the bonded stretching, we see the interaction of two atoms by a chemical bond, B0 being the equilibrium distance, and Kb is the harmonic force constant. For the second term, we see the angle bending. It's the interatomic distance between two atoms in two chemical bonds, and it's the theta being the theta being the equilibrium distance, equilibrium angle, and k theta is the harmonic force constant. And then we have the dihedral torsion, the contribution of the interaction of two atoms when separated by three chemical bonds, and the plane in the chemical bond divides three atoms before and after the plane, and there are two more contributions of Coulombic and Lennard-Jones in the van der Waals potential. So what makes the force field? The potential energy function and the parameters contribute to the force field. So how do we do an MD simulation? First, we give as an input in the system the coordinates and the velocity, which we get in form of PDB in the protein database. We give the chosen force field, put the input parameters, the time step, and the statistical ensemble, and the number of steps. We feed these information into an MD engine, which gives us a trajectory, that is a time evolution, and then we go for analysis for the physical observables. So, post-grain molecular dynamics, in order to study the aggregation process, we need a lot of A-beta peptides and many copies of breakers. So we have used a post-grain molecular dynamics in which four atoms have been grouped into one bead, and these are very difficult to be treated with all atoms MD approach. So for this reason, it is a compulsory. It reduces the degrees of freedom and increases the simulation time steps, which improves performance. So out of the well-known Martini force field is being used in a post-grain. We have used this in this particular model. We see four heavy atoms to form one single bead, and there are many types of interaction sites. So in Martini, one of the drawbacks of Martini model is that the secondary structure switching cannot be seen. So on the left, we see the amino acid mapping, in which each bead in amino acid has been colored differently according to the interaction sites. So since the secondary structure is a crucial in studying the aggregation process, it has been overcome by Go-Martini approach, which is a recent approach which has been published in this paper. So our system consists of 10 A-beta peptides and 50 breakers, which are distributed randomly in a box of 24 nanometer length. And as we see, the number of beads are very less compared to the atoms used. On simulating for 2000 nanosecond, we find that aggregates formation has been taken place for both the system. In a system without breakers, we see a rod-shaped aggregate has been seen. And in the presence of breakers, we see amorphous globular structure. And the rod-shaped structure of A beta is a we can say it's a precursor of formation of protofilaments. And in case of breakers, it's a amorphous globule structure. So and also we observe that all the breakers have been sticking to the A betas during the aggregation process. So the outlook is to, in order to study the aggregation process, we should simulate much bigger systems, backmap to all atom portions of the resulting aggregates, and perform all atoms simulations again, and backmap to quantum mechanical descriptions, inclusion of metal ions, and perform ab initio calculations on small systems. So I would like to acknowledge my group in biophysics group in Torvarata, and INFN and Sineca for giving the facilities. Thank you for your attention.
Okay, thank you for being your time. The session is open for questions. There are no curiosities about this board. Well, then I will start. What is the reason why you have to use this coarse-grained approach? I mean, would it be?
If we do it in all atom, it's computationally expensive, and if we use a coarse-grained approach, it reduces the degrees of freedom, and we can simulate a bigger system in less time.
Yeah, and more or less, what is the computational cost? I mean, maybe you said that, but
Yeah, it's 10,000 crores
for a single.
Yeah, for 10 EBITDAs per 1,000 nanoseconds.
Other questions, curiosities? Well, Claudius, please.
How you build your house grain from the atoms?
Sorry, can you?
How you build your house grain?
So we have this Martinized script which takes randomly heavier atoms, and then they group into one bead. So so all the heavy atoms, 3 or 4, they club into one bead, and so.
Okay, well, then let's thank the speaker again, and let's move to the next speaker of this session. Emiliano De Santis, and he also is coming present from University of Torino. Please. Yes. No? Can you hear from the back?
Yes, okay. So thank you, Francesco. Today I'm going to show you some results on X-ray absorption measurements on high-diluted copper amine complexes. So the outline of the presentation is the following. I will start very briefly with the introduction, introducing you the biophysical problem of protein conformational disorder that is already been explained by Aishwarya in the previous talk. I will focus on diabetes, mellitus type 2, and I will explain how amylin and metal ion have a role in the propagation of this disease. I will describe you the features of the beamline in which we acquired this kind of data, and then I will go to conclusions and sum up. So, as was saying previously, Aishwarya, the protein conformational disorders are a vast class of diseases in which the characteristic is that some proteins became to form aggregates that became insoluble. Today we will focus on the wrong side, on type 2 diabetes and the role of amylin. I would like to stress that even if the proteins that are belonging to this class of diseases are not similar, neither in the sequence nor in the structure, all the aggregates has the same kind of structure, that is the fibrary shape, in which the secondary structure is the cross beta. Is there a pointer? No, okay. Is the cross beta secondary structure. And it seems to be that metal ion plays an important role in these aggregation processes, since they are found quite abundant in the aggregates. The most abundant ones are the copper-2, zinc-2, and aluminium. So, diabetes mellitus type 2 is a metabolic disorder that is characterized by high blood sugar concentration, insulin resistance, and relative lack of insulins. It accounts for the 90-95% of all cases of diabetes and is getting a lot of attention in the sense of the effort to provide possible drugs to stop the propagation of the process, and since it's a severe problem that affects 300 million people worldwide, and since the main cause of this disease is the sedentarity, we can understand that in a few years this number will increase a lot. So it's needed to understand all the processes of this disease in order to prevent the propagation of it. So in the case of diabetes type 2, the protein that undergoes aggregation is the amylin, or islet amyloid polypeptide, that is a neuroendocrine hormone that is long 37 amino acids, and it is co-localized and co-secreted with insulin in pancreatic cells. Among the different functions of this hormone, we can list the glycemic control, reduction in food intake, gastric emptying, and acid secretion. In this slide, on the right, I'm showing the crystal structure of amylin. As you can see, the mainly secondary structure, is the alpha helic, and is also present disulfide bond among the residue 2 and residue 7. And in the sketch, I'm highlighting in red the region that is supposed to be responsible for the amyloid formation. So, different experimental techniques have been used to study the aggregation of amylin, in particular in the presence of metal ions, and it has been shown that the different ions play different roles in the aggregation process. Aluminium 3, it seems to accelerate the fibrillation process. Copper seems to inhibit the aggregation process, while zinc, depending on the concentration, can either increase or decrease the aggregation time. On the right, you can see some TEM images, and the shape of the aggregate is different according to the sample composition. Those lines are the fibrils, and as you can see in the system without the metals and the system with the aluminium 3, the number of lines, the number of fibrils is higher. On the contrary, in the presence of copper, we can see different kind of shape of aggregate that are the so-called amorphous one. So, among the several techniques that can be used to study protein in complex with metals, X-ray absorption spectroscopy is one of the reaction techniques. X-ray absorption spectroscopy studies the behavior of the absorption coefficient MOVI in function of the photon energy in the range of the X-ray beams. So when the absorbing mason is not isolated, the can be modeled as an ongoing spherical wave. This ongoing spherical wave is backscattered by the presence of the surrounding atoms. So the oscillation we see in the spectrum arise from the interference that can be constructive or destructive among the outgoing and the backscattered waves. So in other words, those oscillations contains the information among the disposition and the nature of the atoms that are surrounding the absorber. Among the feature of XAS, the most important is for this kind of approaches of application is that XAS is selective for the absorber. So we can tune the energy of the photons in order to excite a particular atom, that in our case is the metal. And we can study the environment of that particular atom. then the fact that it's a local probe and not crystals are needed means that we can study proteins in their physiological solution. That is the condition that is closer to the real one that is observed in the systems. So the exact spectrum is typically divided into regions. The first one, where the kinetic energy of the photoelectron is low, is called X-rays, X-ray near edge absorption spectroscopy, while the high energy part of the spectrum is called the X-rays, X-ray fine structure region, in which the kinetic energy of the photoelectron is high. The two regions are usually analyzed independently, and the information we can get from each of the two is different. In particular, in the X-rays, since the multiple scattering contribution are prevailing, the analysis is quite difficult, but is richer. On the contrary, since in the X-rays region we can employ the single scattering approximation, it's easier to get information, but those information are mainly among the distances, the average distances of the surrounding atoms. So, in order to get a good quality exact spectrum, we need to have optimized and stabilized photon beam and a good and efficient detector system. The photon beam is usually provided by X-ray sources that are mainly synchrotrons, while for this kind of application, so for instance, the bio application in the bio beamlines, the detection is made usually by using a solid-state detector. But the intrinsic limitation of this detector is that the photons that are acquired, there is an overlap among the intrinsic photons and the ones that are coming from elastic and inelastic scattering. So if we have a sample that is not so dense, we can have this overlap that is a very good, very strong contribution. So a way to overcome this problem is to use this other approach, using CAS. CAS are crystal analyzer spectroscopy, in which we have a crystal that separate, so can in energy with a crystal. So thanks to the Bragg law, we can separate the energy of the photon, and those photons are then collected into a detector. And in this case, we can have only the photons of interest without the overlap coming from the elastic and inelastic scattering. And this kind of approach is very useful when we have a very diluted sample, like the one I'm showing you in a bit. So those are two pictures of the beamline in which we analyze, we capture our data, and as you can see, they are equipped with 5 crystal analyzers that are distributed in a band spherically shape with a distance from the detector that is of the order of 1 meter. In this way, we can have a resolution that is up to 1 eV. So we are very sensitive to the energy of the photons. So the goal of the experiment was to understand if amylin binds to metal ion, and hopefully how it binds to this ion, and in particular if we have a very diluted sample with the concentration of metal of the order of micromolar, if it was possible to acquire good quality SAS data. So the first goal was to see if it was possible to acquire this data, and secondly, if the aluminum that is added in excess to copper concentration was able to modify the copper way of binding to the protein. So the experiments were performed at the SRF in the FAME beamline, and we were the first users to use this kind of equipment for bioanalysis. The samples we acquired, we have three different set of samples. The first one is simply the coupling buffer that it will be used as a reference. Then we have a solution made of copper plus the protein, the amylin protein, and a third set of sample in which we have aluminum added to the solution in which copper is already bound to the protein. So, as a first analysis, we compare the spectrum of the buffer with the one in which copper is supposed to be bound to the protein. And as you can see from the difference from the spectrum, in green we have the copper in buffer, in red we have the copper plus the protein. The spectra are different, so this has the meaning that in the sample containing the protein, copper is bound to the protein and it is not free in solution. So we were able to see copper bound to the protein even if the concentration is very, very low. Secondly, we want to understand if aluminum has an effect on the copper way of binding, and the spectra are similar, but if we do a magnification of the close to the edge section, we see that there are some differences. In order to claim if the presence of the aluminum is able to modify the copper way of binding, we need to have other information, and I will come in a bit to this point. So to conclude, we were able to see that even if the concentration of the metal is very low, we are able to collect good quality X spectra, and this is particularly relevant because what we usually done is to have higher concentration, but those higher concentration can lead to artifacts because we are not seeing what is supposed to be in a lighting system. Then, as outlook, as I was saying, we could employ an ambitious strategy in order to describe and to reproduce the Hexane spectrum in the presence and in the absence of the aluminum. This approach has been already used in the group I'm working in understanding the simpler system in which copper and or zinc is in a solution of pool water. We can use the same approach to study a system in which also the protein is present. Finally, I would like to thank the biophysics group of Tor Vergata in which I worked, the collaborator in ESRF and collaborators in Kili University, and of course, you for the attention.
Okay, thank you, Emiliano. Other questions or curiosities? Well, then I will ask one, which is a perspective one. So what do you think is the connection between the possibility of giving close to physiological condition to potential therapeutical aspects in the long run?
The idea is that once we are close to the physiological condition, we can see what is really in the living system and so understanding what is happening in a system that is close to the living one, we can try to develop some kind of strategies in order to prevent, for instance, disaggregation. So copper seems to be useful to delay or at least to stop or at least delay the aggregation process. So we can think about of using copper in some kind of drugs that we can give to the patients, and then we can stop, hopefully, the aggregation. Of course, it's not so easy, but this is the long-term idea.
Yeah, of course, this is a physicist perspective. Yeah. Any other questions or curiosities for Emiliano? Okay, well, if not, let's thank him again. And the next speaker, with Mario Matan, is invited to come here.
Hello, I'm Mariam Hussein, a PhD student of University Polytechnica Telemarki, and I'm associated to CNR of Rome. I'm going to talk about cobalt palladium-based synthetic antiferromagnetic multistacks on gold resist underlayers towards biomedical applications. So as we know that magnetic particles are widely investigated for applications in hyperthermia, MRI, magnetic separation, drugs and gene delivery, magnetomechanical destruction of cells, and biosensing. So due to the small size of these particles that usually ranges from a few nanometers to few micrometers, thus they can be smaller or comparable to a cell or a virus or a gene. Thus, they can interact with biological entities at the cellular and molecular levels. In addition, magnetic particles can be resonantly manipulated by an external magnetic field, thus they can be transported, immobilized, and rotated. As well as they can generate heat when they resonantly respond to a time-varying magnetic field. In addition, magnetic particles can produce magnetic field, thus they can serve as contrast agents for magnetoresonance imaging. Thus, a particle for biomedical applications consists of a magnetic core that I will concentrate on and our attention will be focused on, and a biocompatible coating which can be functionalized differently to perform different tasks. So, for a magnetic core to find applications in biomedicine, it should fulfill some criteria, including a high magnetic moment. This allows efficient manipulation of magnetic nanoparticles by an external magnetic field. In addition, it should have a sharp switch to saturation magnetization, which allows more efficient access to the saturation state, and a zero remanence, which is the magnetization at zero field. So this prevents the particle agglomeration, and this ensures the stability of the particle suspension, as well as it should have low susceptibility at small fields, which prevents the particle agglomeration due to the magnetic moment induced from magnetic fields from the environment. Thus, to find applications in biomedicine, we should have an aqueous suspension with stable particles fulfilling these criteria. When the size of a ferromagnetic particle, first, in a ferromagnetic particle with large sizes, a multi-domain structure is energetically more favorable. However, when the size is reduced, a single domain structure becomes more energetically favorable. Further reduction of the size could lead to enter a superparamagnetic regime, where in this regime, due to the thermal agitation, the magnetic moment can flip between the anti-parallel easy axis and to be superparamagnetic. So, and as we can see, I forgot to see, so here, as we can see from the magnetic response, magnetization versus field hysteresis loop, these superparamagnetic particles can be studied for biomedical applications. However, they still have a high susceptibility at low fields. These magnetic particles can be produced by chemical synthesis with different shapes. However, it's difficult to produce large numbers of particles with controlled shapes and magnetic particles and sizes with these bottom-up approaches. In addition, the magnetic moment from these superparamagnetic particles is usually low. So in order to try to increase the moment by increasing the size of the particles, this could lead to exit from the superparamagnetic regime, and this causes aggregation of the particles, and thus we lose the stability of the aqueous suspension, which is not good for biomedical applications. On the other hand, top-down approaches, which are based on combining lithography processes and etching processes, where first sacrificial resist layer is deposited on a substrate, and then the magnetic film is deposited on the resist layer, sacrificial layer, And by combining these lithography techniques and etching processes, the magnetic particles are prepared, and after dissolving the sacrificial resist, we obtain freestanding particles. These top-down approaches have been used to prepare vortex microdiscs, and as we can see, the hysteresis loop, the M versus H curve, is similar to that of superparamagnetic particles, where we still have high susceptibility at low fields. An alternative is to use synthetic antiferromagnetic microdiscs, where, however, most of the research is concentrated on using in-plane SAF microdiscs with in-plane magnetic anisotropy. And as we can see also, we still have as superparamagnetic particles and as vortex microdisc a large susceptibility at low fields. So we are still need to optimize. So an alternative is to use a synthetic antiferromagnet with a perpendicular magnetic anisotropy. Because, so first, what is a synthetic antiferromagnet? A synthetic antiferromagnet is made of two ferromagnetic layers separated by a metallic non-magnetic spacer. And by varying the thickness of this metallic spacer, we can either couple these two layers ferromagnetically or antiferromagnetically. And when these, as we can see from the M versus H of a SAF with perpendicular magnetic anisotropy, here we can see a response that is suitable for biomedical applications, where the magnetic moment here can be tuned, and we have zero remanence, zero magnetization at zero field, and we have zero susceptibility at small fields, and we have a sharp switch to the saturation state. And here, and okay, as we can see also that for a SAF, we have first, starting from a high saturation magnetization, the two magnetization in the two layers are aligned parallel to each other. Further reduction of the field will lead to flipping of the magnetization on one layer, so we obtain this antiferromagnetic response at zero field, and further reduction at negative saturation field. The two layers will align also parallel to each other. As I explained, these synthetic antiferromagnets with perpendicular magnetic anisotropy fulfill all the criteria, including zero remanence, sharp switch to saturation magnetization, low susceptibility. In addition, the moment can be tuned without affecting the other magnetic properties. So, to add to this domain, we have prepared the multi-stack thin film, which was deposited first. We deposit a sacrificial resist on a substrate, serum thermally oxidized substrate. And then we deposited the film stack. We varied the repetition number M, which is the number of the SAF units. And we deposited gold for functionalization. So our synthetic antiferromagnet is made of cobalt palladium multilayers, because these multilayers show a very high perpendicular magnetic anisotropy. Here we have the in-plane magnetic anisotropy, so we don't see any hysteresis. So these cobalt palladium multilayers are suitable to have a large perpendicular magnetic anisotropy. To optimize our SAF, we varied the ruthenium thickness, which is the metallic spacer here. To have an antiferromagnetic coupling, we observed with a ruthenium thickness of 0.4, we could obtain, here the blue one, antiferromagnetically coupled layers with strong perpendicular magnetic anisotropy. See also here from the in-plane hysteresis, there is no hysteresis loop. So then we deposited this SAF unit on gold resist to study the effect of interface. So we obtained a strong antiferromagnetic coupling with a strong perpendicular magnetic anisotropy, which makes these suitable building blocks to prepare multi-stack thin films on gold resist. So after that, after optimizing the SAF unit, we deposited the multi-stack thin films on gold resist, and we varied the number of repetition of the SAF units. As we can see, our thin film stacks fulfill all the criteria necessary for biomedical applications, including zero remanence, zero susceptibility, and sharp switch to saturation magnetization. In addition, when we vary the number of repetitions, we can vary the magnetic moment without affecting the other magnetic properties. However, okay, as we can see with M equal 8, we have deterioration of the magnetic properties. As we can see, to see the reason behind this deterioration, as we can see from the DEM image, as we increase the number of SAF units, we see an increase in the interface roughness, and this is the reason behind this could affect the layer quality. So in the final step, we have to produce these SAF microdiscs. We produce an array of SAF microdisc particles by combining electron beam lithography and ion etching. As we can see from the preliminary test, we have a sharp switch of typical two reversal step or typical of a SAF. And in conclusion, so our preliminary tests indicate that the microdiscs can be obtained without significantly affecting the magnetic properties. However, further work is necessary to improve the lithography processes. And thank you for your attention.
Thank you for this very nice talk. And are there questions from the audience? I know it's the last session, but please don't be shy. Well, oh, there's one. Great.
Hello, thank you for the nice talk. It was really interesting. I'm just curious, in what kind of fields can we use this magnetic nanoparticles? So they can deliver something or accumulate somewhere. Or...
Okay, this is a preliminary work, but we are still first we are trying to optimize our thin films, our particles, and then we can find these applications. But as I mentioned before in the slides, this can be useful in hyperthermia, drug delivery, and other applications. But for as preliminary tests, we are aiming to optimize our films to fulfill the criteria necessary for biomedical applications.
Any other question? Curiosity? This not being the case, let's thank Mike again. And let's move to the last but not least speaker.
Thank you. First, thanks to organizers for letting me speak. Having been heard me last year, but still they allow me to speak. And my name is Mihir Durbe. I'm a PhD student at University of Trieste, and I'm also affiliated with Abdul Salam International Center for Theoretical Physics in Trieste. I'm privileged to be a student of these two great scientists, Professor Antonio Ciolani in ICTP and Professor Fernando Peruani in University of Nice. We are fascinated by systems something like this, like a flock of Stirling frogs. In Rome, you have witnessed this Stirling flock. So thousands of birds, they come together, they flock together, They show some spectacular aerial maneuvers. And it's not only about the birds, but some kind of systems of fish, they form vortices, bacteria, they form colonies, they even bacteria swim in the some liquids or like in our blood, or even the human crowd or the penguins. I took the picture of penguin because there are no privacy issues. So we are interested in these kind of active systems. And the question we ask is one of the questions in this field that we ask, how these agents interact with each other to show this collective behavior. So is there any leader? So all the agents follow some leader, or everyone takes his own decisions. So how they really do it? So a bird in a flock cannot interact with everyone, but somehow they stay together. Somehow they show this collective behavior. So here's the question that we try to ask. It's one of the questions in the field. And to answer these questions, if you open, there are many models which are proposed. So models are basically what we think that the agents are doing. We put them in a mathematical form, and then we check if it tallies with what we are observing. So these are some notable models. Without going into details, I just say that with inelastic collisions, people saw that agents can form vortices. With interacting spin, people say that okay, birds can turn in a group together. So these are just the technicalities, but these models have some limited success in explaining some observed behavior, but not the all behaviors. Some of the algorithms are really even made to look complex like that. So in 82, it's a long time ago, scientist Aoki explained with this kind of complex algorithm that how the fish stay together. No wonder if they follow this kind of algorithm, it is called the school of fish. So, one of the notable models in this field is called the mid-check model, which is the simplest, and it answered one question that these agents without any apparent leader can stay together as a flock and move together without any leader. So I just explained in a brief that what the model is algorithmically. So in simulation, computer simulation, we take a box of size L by L, and each agent is shown by a black arrow here. So it has a circle of radius r centered on it, which is called the interaction radius. So it experiences the other birds or the agents in this radius. And what it does that it computes the average direction of its neighbors, and it moves in that direction with some noise. So with this simple model that we see that this agent can flock-like state when the noise is very low. So this is our in-house simulation, which is just following this rule. And we see that these agents starting from some random configuration, they eventually form a flock together and move together. So the point to note is there is no leader, but everybody is sticking together with just this simple rule, with this simple model. And if the noise in the system is very high, then we see that they don't flock together. They are just the random walkers. And Witcheck et al. Just showed that from here to here, how you go when the noise is increased. It's a phase transition with some order parameter, which is not at the interest at the moment. I'll come back to it later. So our approach is different. So our approach is, okay, there are various models with a varying degree of success, each explains something. So why not we treat these agents as the decision makers? And so the first target is to just make this artificial group of robots or artificial agents to flock together. And from that, at least we know that we use machine learning techniques to make them flock together. And then we can say what they did, we can say something about the real systems that, okay, if the artificial agents are doing this policy, maybe the birds are also observing this policy. So to use that, we use reinforcement learning technique. It's one part of the artificial intelligence. And the scheme is roughly as the following. So you have the agent, and it takes action in its environment. So for example, if I'm a robot and I just want to learn to get out of this room, so I take actions to go left, go right, go up, go down, and the environment in turn for my actions gives me a new state and the reward. So the state is when I move with respect to door to the other position, and the reward could be the inverse distance from the door. So my goal is to learn to take actions in a state so that I optimize the reward, so I can learn to get out of the room. So how we set up this our problem in this framework? So again, we have some agents. This is the agent with its fixed frame of reference, and we discretize the direction it can take in just 32 for the algorithmic purposes. So at each step, these agents compute the average direction of neighbors, which is again the circle R, and it is one of the discretized directions. So we say it has some label, it's 30. So this is a state for my agent, and it choose to take one of the action by some policy, and that part I will come later. So it can choose any of the actions to move, and then it moves in that direction. And the environment in terms give the reward as the following. So we set this reward, and the reward that we set is just to aggregate. So for the agents to flock, we just say, okay, the aggregation is good. So if moving from time t to time t plus 1, if it reduces the number of neighbors which are in this neighborhood, then we say no, it's not a good move. And if the number of neighbors remain the same, or if they increase, we say, okay, it's good. So we give it a positive reward. And this reward is just a real number in a algorithmic case. So what agent really do with this information? You get a state, you select action, you get a sequence of reward. So now it has to learn that, okay, I was in some state, I took this action, and I got this reward. And this is done by what is called the Q algorithm. So each agent has its matrix, which is a state action pair matrix, and it updates the value in this Q matrix for given state and chosen action with this formula. And this is alpha is called the learning rate. So it keeps doing iteratively this stuff, and at the end we have some expectation that at the end, if you keep doing this training, at the end every agent has a notebook which is the optimal one. So it knows that in which if it measures the state, it knows which is the best action to be performed, which will be the highest quality, highest value in this quality matrix for the given state. So what this training looks like. So in the beginning of the training process, it's just a farrago of agents. So they are trying many actions, they are just getting the reward, and they are trying to update their Q matrix. So we let this happen for many iterations, some episodes. And in the end, what we see that this is learned behavior. So in the end, they start to do this thing. Okay, this is what the interesting point is. And so as the training goes on, we just plot this reward, and it touch the optimal value. We compute it in some different way, but we are sure that this agent will learn something, and they learn to learn the policy which gives them the optimal reward. So the interesting question is now what policy they learn. What do they learn for this aggregation? So this policy is which optimize the aggregation of the agents. And when we open the policy, we open this Q matrix, which is 32 by 32 with the action labels and state labels. And this plot indicate the state, the action for which it has a maximum Q value for the given state. So we say that we see that it's a diagonal. What it means that if you are in a state 3 in this picture, you take action 3. So you measure the average neighborhood direction, and the best action is to turn around that one. So this is what the check model is, which comes out as the optimal one. And then we measure another quantity that it's called the polar order parameter. It measures that it's a measure that measures how many agents are in the one particular direction. So this value is 0 if everybody is randomly oriented, and this value touches 1 when everybody is going in the one direction. So we see that as the training episodes go on, this order parameter tends to be 1. So they are just moving like a flock, they are just going in the one direction. The conclusion is that we ask for the multi-agent system to optimize over aggregation. Just the number of neighbors you have to optimize. And in return, what we get is not only the state which has the maximum aggregation, but also they move in a parallel direction. And one of the policies that comes out is like a win check like policy. So we can say that the win check model, which is considered as a toy model, but it is also optimal for the reward of just aggregation of agents. So for agents, it's a little easier than to compute average directions and turning just to optimize over the number of neighbors. And I thank my lab mates, Matteo and Alberto, and I thank you so much for your attention. Thank you.
Thank you, here. Are there questions or curiosities for this nice application of physics? There's one, Luca, please.
Hello, thanks for your interesting presentation. I'm just like interested, does the like learning rate or does the learning time depends on the count of the particles?
Sorry, can you say again?
Like, does the learning episodes like depends on the particles number? So like, how many particles are we like?
Okay, so you mean I tried it for one system size, that's 100 agents, but on the other hand, extremely we tried for the one single agent, which has a in the background, which is there is already a flock. So we wanted to see that whether this learning agent will learn to flock this strategy, which is already put by hand, and then you take a less number of episodes to be trained. Because this environment is already in a one stationary state, which is already going ordered state. So here it takes some time for some episodes for agents to converge to a policy. But I really don't know if I double the number of agents, whether this will decrease or increase the number of episodes it will take.
Okay, thanks.
Other question? Is there anyone going to? Maybe the last question of this meeting. So that's a honor.
Thank you. What's somehow related to the other one. I understand. So the reward is that let's say the number of neighbors increase, but how is the neighborhood defined? Is there still a metric verification or not? I mean,
Fixed
distance?
Yes, fixed distance.
So the each ingredient is somehow there.
Yes. Yes.
Because this is, that is what gives let's say, it's not an optimal number somehow. You can increase unboundedly.
Yes, you can change the radius and then again it would be something different. I don't know. I tried with some range of radius for which it is showing the robust result. But then the question is again, if I put the topological model where they interact with fixed number of neighbors, that is something different. But then I cannot put the same reward because in topological you fix the number.
No, it would be nice, for example, to check because it doesn't seem that you get a collapse in the end. So if you measure, for example, the distribution of the neighbors within that distance, it will be interesting to check if it's equal to the expected number for the topological interaction model. Like if you do a probability distribution of the number of particles that are in the
Yes, that's correct. And also, just on the point that why don't they collapse on one point, because this reward should allow it. The one thing is that it's a correlated system. So when you try to go near to the another agent, you're losing the neighbors on one hand side. So that's the one
reason. That would be interesting to see if in the end you pick up the optimal number.
Exactly. Yeah, that's our one idea in our mind, that to figure out that what's optimal way to talk to each other, and how many agents you should talk. That's correct.
Thanks.
Very good point. Thank you.
Okay, well, it's nice to see that the discussion is still lively after 4 days of meeting, which I personally find a success. So with this, with me here, we end the scientific sessions of the meeting. And now please don't leave because Lorenzo Aiello, as part of the local organizing committee, will give us concluding remarks and most important, also present the prize and stuff like that. So, just a second. Please, Lorenzo.
Okay, thank you. Okay, just a slide to conclude this conference. So, you know how things proceed to the conference. We start with the first day with all the attendance and then progressively the closing, but it's nice to see that now that we are at the final session, there are more people that in this should come pictures. This has been due to also the fact that this has been the most successful young research meeting ever. You can see here the number of participants that we had during all the previous editions, starting from the first here in Torregata in 2009. And for the first time, we were able to overcome the threshold of 100 of participants. In order to be precise, 110 participants to this edition. In order to give you some numbers, we received a lot of contribution, and we were able to schedule up to 42 talks divided in 10 different sessions, but also the 2 invited talks that we thanks to the invited speaker to give them to give their contribution to the conference, and also the speakers of the roundtable with the connection between physics and industry that we had during the first day in La Mondragone. Moreover, for the first time during a young research meeting, we organized multiple poster sessions. In this way, we were able to accept up to 44 posters that has been divided in the first poster and wine general session that we had the first day in La Mondragone, and then the parallel session, poster A, session A, session B that we had here in Tor Vergata in the last 2 days. We had during the different poster session, both in Villa Mondragone, both here in Tor Vergata, a lot of participation and interaction among the different attendees with a lot of questions, and this has been done also during the different talk session. This also thanks to the high quality of the presentation that has been presented during the meeting. This is just some of them. And as in the previous edition of the Young Research Meeting, we had also different social events, like the tour of Villa Mondragone the first day, the social dinner on Wednesday evening. Yesterday you had also the visit to the Frascati National Laboratories. This will conclude this afternoon with the guided visit to the Grand Center Rome. Then an important remarks, you know that now is holiday times, not only for you, but maybe for also your professor, your colleagues. So keep in mind that for proceeding submission, the deadline is July 15 in order to not risk to arrive at the very last day. And you will find on our website all the instructions that you need in order to properly submit your proceeding. Then, this is the local organized committee that organized this conference, and in order to conclude it, I would ask to all of them to come here on the stage to finish the conference. Please. We have seen all of us at the registration desk as chair during this day, so the spaces are quite familiar. I wanted to introduce them one last time, thanks to Luca, Silvia, Francesco, Marina, Elisa, Giorgio, Rocco, and Emanuela. And I think we have done a good work, and I hope that you have found a good conference. But if this logo is now well known, what is still a mystery is what will be the next one for the next edition. We are still waiting, still looking for a location and a local organized committee. We received up now 2 possible candidates for next year edition that could be Bologna or Trento, but if you think that your university or your institute is able to organize an edition, feel free to submit your proposal. You can do this, keep in contact with us with our social media, in which you can have news about the meeting, you can ask for picture of this meeting, you can watch again all the talk that has been recorded on our YouTube channel. You will find the link to our all social media on our website. Then, a last thanks is mandatory to our sponsor, the University of Tor Vergata, the National Institute of Nuclear Physics, the Piano Laurea Scientifiche, the Tor Vergata Solar Physics Group, and the ACA companies for the support, as the Tor Vergata University, the Frascati National Laboratories for their hospitality, A great thanks to the Secretary of the Science and Agraria, the Department of Physics for their support in the logistics, and all the invited speakers for their contribution. And last but not least, thanks above all is to all of you to bring us your because you are the strength of the conference, because without you, the conference would not exist, essentially. So thank you to bring and shared with us the passion that you have in your work, and hope to see you again in the next edition. Thank you very much. Now, the moment that most of you waited for, the beginning of the conference.
Your life.
Okay, I have to admit that it has been tough because the poster level was very high, so we were quite in trouble, but you know, it being only one winner, luckily, very likely. And so the best poster award is to Jessica Cagnoni for modeling the snow avalanche using cellular automata. That if she's here, I asked to come here on the stage. Thanks. That we receive the certificate for Giorgio, please.
Wait for the picture.
Okay. Again. One more. Please. Okay.
Now Luca will give you some service this afternoon.
Okay, so now we have lunch break, and all the people that are going to the to visit the city center with our guides have to wait so that we can move all together with the public transportation. So we meet at half past 2. I think we will move from here more or less half past 2. From here, from the lunch break room. So please wait there if you want to join for the visit. And thank you all again for attending the meeting.
Un saluto agli spettatori. Ciao.